Welcome back. In the last class, we saw how we can calculate the J coupling pattern based on the number of hydrogens to what a given hydrogen is coupled. So, this was using this Pascal triangle which is shown here. So, we can see that if there is one hydrogen coupled to one hydrogen, we got a doublet because of the splitting, and that gets split because of into two into equally half signals. So, you get 0.5, 0.5 which has a ratio of 1:1, the relative intensity. So, you can further split the signal into two more signals in case there are two protons to which this hydrogen is coupled. So, you get further 3 peaks, but remember the center peaks from here and here they combine, therefore, instead of 4 different peaks we are getting actually 3 peaks because the center peaks of the two splittings they combine. So, you get 0.25, 0.5, 0.25. So, you get 1:2:1. So, in this manner you can continue further and see what happens if there are 3 hydrogens coupled to 1 or 4 or 5 or 6, and in this manner you can continue to calculate the different splitting pattern which will give you the different relative ratios. So, the main point here is that we are looking at relative intensity ratio which is shown here. So, if I have a peak 3 peaks which are 0.25, 0.5 and 0.25 ratio, it becomes 1:2:1. So, this is a triplet because there are 3 peaks. So, you will have a quartet, you have a pentet, you have a sextet and so on, and that is how the splitting pattern goes around goes about. So, we can continue with this J coupling today and see what are the different more important points about J coupling, how they can give us information about structure and so on. So, one thing is that what we saw in the previous slide is that the hydrogen atom A had the same coupling value to the different hydrogens. So, that is why the n+1 rule is applicable, but that is not always the case. If a nucleus is J coupled to more than one nucleus of different types of different values, then you will have different J values. So, example, let us see here, suppose we consider a hydrogen atom A, it has a coupling J1 to a hydrogen atom which is 3 bonds away C, and or it has another coupling value J2 to another hydrogen atom on this side. So, you see these two J values are not the same now. So, therefore, if I consider this hydrogen atom as 1 and this hydrogen atom as 2, so this hydrogen will not be split into 3 peaks, n+1 rule is not applicable here, the reason being that each J value is not the same. So, in such a situation, how do we calculate the coupling pattern? So, this is shown here. So, what basically we have to consider is like this. So, first you start with 1A, this is one hydrogen atom which is unsplit, which is one line. Now, when you consider J1 coupling, it will get split into 2. So, that is why it is 0.5 and 0.5. Now, because of the second J value, that is J2 here, each of this peak will be further split into 2 peaks. So, now it has each peak here. So, this 0.5 becomes 0.25 and 0.25, and the separation between these two lines is now J2. Similarly, this peak which was split because of J1 gets further split into 2, and you can see here the splitting distance is now J2. So, therefore, these two central points, so the main point here is these two lines here. In the earlier slide we saw that they collapse, they combine and they join and become 0.5, but here they remain separate, and the reason they remain separate is because J1 and J2 values are not the same. If J1 and J2 were same, then these two lines would have become combined into one because they would have come close to each other and they would have actually come at the same position. Because of this difference in J1 and J2, they no longer come at the same position. So, they are separated, and instead of 3 peaks, now we end up with a 4 peak pattern. Then what is the relative intensity now? The relative intensity is 1:1:1:1. So, all of them are equal, and that is what is shown here. So, this is called a doublet of a doublet. So, basically the original peak gets split into doublet because of the bigger coupling, and then further it gets split into smaller couplings because of another coupling, and that is doublet further. So, we say a doublet of a doublet. So, the main point to remember here is that you have to first consider the bigger coupling value and then go to the smaller coupling value. So, decide first which is the bigger value, I mean if you know the value, and then based on that you split it first, then take the smaller value and split it further. So, this can be continued if there was J3 another coupling to A, let us say one more atom here could have been J3 and so on. So, you can do this n number of times by simply considering this kind of a diagram, which is for the Pascal's triangle. So, now J value we can look at the exceptions. So, this is what we saw in the earlier case, that in this case if these two hydrogens, suppose that X and Y, they are not the same, then in that case these two hydrogens are not similar, and therefore, this value, this will be split by this hydrogen and this hydrogen will be split by this hydrogen. So, basically the point here is the protons which are not equivalent, they split each other. So, that means if they are equivalent by rotation, then they do not split. So, what is shown here is the methyl group. So, if you see in a methyl group, they are chemically equivalent because of fast rotation, and because they are chemically equivalent because of fast rotation, this hydrogen do not split each other. But remember that it is not that there is no coupling between these two, there is a coupling, but we cannot see it in the NMR spectrum. If therefore, that means between any two hydrogen atoms, if they are chemically equivalent, then they will basically not split each other, but does not mean that there is no J coupling. It is just that the NMR is not capable of revealing the coupling between two equivalent hydrogen atoms. So, the methyl groups always will come as a single entity, but if they are coupled to another hydrogen here, then they will be this hydrogen will be split because of 3 into a quartet. So, this is what we saw in the last class, but if you look at these 3 together, they do not split individually each other within this methyl group. So, methyl group protons are equivalent. So, there are different exceptions to this n+1 rule. We saw already that exception basically based on the coupling value. So, for example, if you look at this hydrogen here, this particular hydrogen, this has one hydrogen cis coupling here, one value, but it will have a trans coupling to this hydrogen, another value. Similarly, it will have a coupling to this hydrogen, some other value. So, you see what happens is there is one here, one here. So, if you ignore this hydrogen, so let us ignore this hydrogen for time being. Even if you consider this hydrogen's coupling to this and this, you may think that there are two hydrogens. So, its coupling to this will be n+1, that is triplet. That means, this hydrogen you may say that it may expect as a triplet, but that is not correct, because the coupling of this hydrogen to this hydrogen is not the same as coupling of this hydrogen to this hydrogen. So, therefore, this hydrogen will show a doublet because of this and another doublet because of. So, doublet of a doublet will come for this particular hydrogen and not a triplet, that is 1:2:1, what you expected if you use the n+1 rule. So, this is basically the different ways of examples how the n+1 sometimes applies, sometimes it does not apply. So, we can go this further and then to get the different cases where there is an exception to the n+1 rule, but all these cases they are equivalent hydrogens. So, when they are equivalent hydrogen, you do not expect a splitting. So, that is what the point here is, that these two hydrogens are chemically equivalent. So, they will be split because of the fluorine. Similarly, here the two hydrogens are equivalent. So, you do not see a coupling within these two. Remember, these two hydrogens are geminal coupling, they are coupled to each other, but you do not see the splitting because they are chemically equivalent. Okay. So, this is basically the idea of the J coupling, that whenever you have a chemically equivalent hydrogens, they do not split each other even if there is a coupling between them, because they are equivalent. So, we do not see them in the spectrum. So, J coupling actually depends on many, just like we saw in the case of chemical shifts, the J coupling also depends on a variety of factors, and this is what a few factors are listed here. Of course, this is not straightforward to calculate J coupling in any particular molecule. There are a lot of software programs and there are some electronic calculations has to be done, but nevertheless some basic rule of thumb or basic rules are there. For example, it depends on the gyromagnetic ratio of the two nuclei. So, you have, suppose you have two hydrogens, the two hydrogens coupling will depend on the gyromagnetic, which is same for both, but if you look at hydrogen to carbon, it will be less if you have, because the carbon gyromagnetic ratio is less. That is number one. Number two factor is, it also depends on number of bonds which are separating. So, if you have the hydrogen bonds separated by two bonds, which is called geminal hydrogens, they will have a stronger value of coupling compared to a vicinal hydrogens, which is 3 bond separation. If you go for longer 4 bond, 5 bond and so on, the hydrogen coupling becomes weaker and weaker. Of course, one bond hydrogen is not there. We talk about one bond hydrogen to carbon. which is very strong because it is one bond. So, the number of bonds which are separating two atoms matters for the coupling. So, this is not generally, we are not talking about only hydrogen coupling here, we are talking about hydrogen to X, that is heteronucleus like carbon, nitrogen or any other. So, this is a general concept for any J coupling in general. It depends on the hybridized conformation of the molecule, that is the structure of the molecules, because we will see shortly that the 3 bond hydrogen coupling depends on the dihedral angle between the two vectors. We will look at that. It depends on the hybridization state. So, sp2, sp, sp3, this different type of hydrogen, this is in terms of carbon. We are looking at carbon proton coupling, there it will matter, but depending on the hybridization state of the carbon. Similarly, it also depends on the substituents attached to carbon. So, these are some of the few basic points. As we go further into heteronuclear NMR, we will encounter this more. Right now, we are focusing only on proton-proton coupling. So, typically the different coupling values are given here, and this is very general typical values. So, you can see that proton to carbon is about 110 to 270 depending on variety of factors like the hybridization state and substituents and so on, and these are ballpark numbers. We do not have to go into detail, but this is idea, it will give you the different values. So, the hydrogen couplings, I mean the vicinal and geminal are not listed here, that will come up in the next few slides. So, this is what is shown here. So, we have what is called 2 bond geminal coupling was that is, so the typical notation we use in NMR, you write like this. So, the 2 is a superscript, J coupling is written like this, that means 2 bond hydrogen coupling, and you know the geminal coupling can have a negative value or it can have a positive value. So, couplings can always, remember, have both positive and negative value, although from a simple 1D NMR you can never find out the sign of the coupling. So, that is why 2D NMR and other more techniques are available to find out the sign of the coupling, sign meaning whether it is negative or positive. But a simple 1D NMR will, the coupling, the splitting, the multiplet peaks which we see because of coupling, that from that you cannot figure out whether it is a negative or positive coupling. So, these are some values given here for different systems. So, the main point here is that it depends on the bond angle between the two hydrogens. So, this is for the geminal coupling. It depends on the hybridization state of the carbon and substituents. So, these are the main 3 factors which influence the J coupling in a case of geminal coupling. When it comes to vicinal coupling, when you talk about say vicinal 3 bond coupling, means 2 hydrogens which are separated by 3 bonds, 3 covalent bonds. So, this is shown here. So, you can see this hydrogen and this hydrogen are separated by 3 bonds which is shown in the red color. So, here we do not talk about bond angles, we talk about torsion angles or dihedral angle. So, this dihedral angle is shown pictorially here. So, you can think of it as an open notebook, a plane which defines these 3 hydrogens, these 2 carbons and a hydrogen become one plane, and this particular proton and these 2 carbons become another plane. So, you can see that these 2 planes are now at an angle with respect to each other, and that angle we call it as a torsion angle. So, there is a very famous equation known as the Karplus equation which shows how the J value, the 3 bond J value is related to the torsion angle. So, this is typically the equation. So, this is A cos square theta plus B cos theta plus C, and here the values A and B depend on the type of J value you are looking at. So, in a particular molecule you will have a variety different types of 3 bond J couplings, vicinal couplings, and for each that kind of typical type of those couplings we will have to empirically experimentally determine, or based on the different values measured experimentally we can figure out X by fitting the value of A and B and C if we know the structure. So, this is what it shows here. So, you can see from this equation one thing is, if I know the torsion angle, it does not give me the J value uniquely because there is a quadratic equation. So, a quadratic equation will always have 2 solutions for phi. So, if I know the J value from experiment, it does not mean that I can calculate uniquely the phi value, because this is a quadratic in phi, the angle phi, and therefore, it will have 2 solutions. So, there is always a degeneracy. So, which is shown here. For example, this particular J value, if you take this particular say 6-7 hertz, you see it has 2 or 4 possible solutions. Of course, they are related by 180 degree rotation, but you can see there are two possible values which will satisfy this J coupling. So, this is one of the very famous equation which is used for given a phi value to calculate J, or vice versa, given a J value at least estimate what could be the bounds, what could be the values, possible values of the phi. So, this is further continuing on the effects that depends on the effects of the substitution, substituent effects depends on the structure of the molecule, and you can see here that in aromatic compounds there are long range couplings and the ortho meta para couplings between the hydrogens are different. So, now that we have come to the end of the first part of this course, in the first part of the course we saw seen the different concepts, what is a spin, what is a rotating frame, what is chemical shifts and so on. So, what we would like to do in the next 15 minutes or so, let us recapitulate what we have learnt in the first part, because from the next class onwards we will be moving on to more advanced topics, that is actually how to analyze, interpret NMR spectrum, how to record a spectrum. So, let us recapitulate the basics what we have learnt in the last few classes. So, this is what is shown here. So, we have basically seen these are the following different aspects we have looked at. We have looked at nuclear spin populations, we looked at rotating frame, relaxation, free induction decay, and we looked at what is chemical shifts and how what is chemical shift equivalence, and then what are the different factors which affect chemical shifts, and J coupling. So, what we will do now is just go through each of this and quickly see what are these concepts, so that this will be we will not be relooking at it again as we move on further. So, nuclear spin population starts from basically looking at how the spins are oriented in the magnetic field. So, when you do not have a magnetic field, the spins are degenerate, the two spins which are oriented alpha half plus half and minus half, they have no particular orientation, but when you apply a magnetic field you see that the spins get split into two populations. This is called the lower ground state population energy, ground state energy level, and this is the upper state energy level. So, this happens when you take a collection of molecules in a magnetic field. For example, let us take a glass of water, you put it in a magnetic field, then the spins in the water, the proton spins in the water will now get distributed between two states, that is what is shown here, the ground state and the upper state. Now, if you look at the energy difference between the two states, we call it delta E, and for to achieve that excitation, to go from lower state, take a molecule from lower state to an upper state, that is when you want to flip a spin, you have to apply its energy delta E, and that is applied as a electromagnetic radiation, we denote it as h mu. So, we can calculate this, what is this delta E is going to be, and that comes from this formula, that whenever you have a spin which has a charge, a nucleus remember has a spin and a charge. So, it has a magnetic dipole moment, and that is mu, and that interacts with the magnetic field B, and both of these are vectors. So, we take a dot product, and that dot product turns out to be this, if you consider that the B0 is applied in the z direction, and this is what we get, this is the energy value we get. And you can see that if you have an alpha state, that is when spin is plus half, you essentially end up with this. Remember, in this all these equations we use this h cross or h cut, which is basically the Planck's constant divided by 2 pi. And if you have a beta state, the molecules which are in the upper state, they will have an energy given like this, but minus into minus cancels out, so it becomes plus. So, this is a positive energy value, this is a negative. So, what we need to find out is the difference between the upper energy and the lower, that is the difference in the two energy levels. So, if you calculate this value, it turns out to be delta E is equal to this value, and that is equal to the energy we want to supply, that is the energy here, and that if you calculate, this energy is nothing but gamma into B0 over 2 pi. Now, remember in radians, when you want to measure in radians per second, that is in the angular units, you multiply this 2 pi with this mu, and that is nothing but omega 0 equal to gamma. So, this is a famous central equation in NMR, which we saw in the very beginning, where we see that the energy required, that the frequency of the excitation required to go from ground state to upper energy state is basically given by omega is equal to gamma B0. This is the most important relation in NMR. Now, if you look at the population wise, so what happens is, according to the rule known as Boltzmann's law, here it says that the two energy levels are not equally populated. So, there are more number of spins in the ground state and less number of spins in the upper energy state. and this ratio of the population between the two states is given by this law, Boltzmann law, which is related to minus delta E over kT. So, there is a kT here and that is what is shown here. So, this is e raised to minus gamma h b 0, in our case is a B magnetic field divided by kT. So, in the next part we saw how this rotating frame of reference is important in NMR. For that we have to go into the classical picture. So, this is what a classical picture says, that imagine that you have a spin nucleus having a spin which is pictorially represented like this. So, when you put it in an external magnetic field which is oriented along the z axis, the spin starts precessing, revolving around this magnetic field, and that precessional speed, that is angular frequency of this spin is given as omega is gamma b 0. So, this is the same equation what we saw in the previous slide. So, the point here is that in the quantum mechanical point of view and from the classical point of view, the energy is the same, because we are looking at the same system. So, now if you now look at a particular spin, if it has an alpha, if it is in the ground state, it will be oriented like this, and if it is in the beta state, it will be pointing downwards. So, if you now take a large number of nuclei, remember we do not deal with 1 or 2 nuclei or spins, we have a collection, we have a for example, if you take a water 1 ml of water, you have a huge number of spins, and that 55 molar is the concentration, and that is this, you can see they are represented like this. There are large number of arrows which are spread over this magnetic field, and all of them are precessing. So, that is not shown here, but you have to keep in mind that all these spins are precessing or revolving around this magnetic field, but they are not together, they are spread distributed over this cone, and this is called as a random phase approximation in NMR, and this is what we saw in the previous classes. And now similarly, if you have alpha state, you have spins pointing this way, and in the beta state the spins are pointing downwards. So, now what if you do a vector addition and subtraction, we saw that the xy plane, whatever, if you take a projection of this vector for example in this direction, there will be something else here which will come in this direction. So, they will cancel each other. So, if you look in the xy axis direction, the spins all cancel each other, but what happens is you have a vector addition, the net addition happening in this direction plus another addition in this direction. So, you have a net vector in the z axis, positive and negative z axis. Now, they will start cancelling each other, and because there are more number of spins in this side compared to this side, the vector addition on this side will be higher, stronger, and therefore, you will get a positive z value after subtracting the z part and the minus z part. So, this is what we call it as a net magnetization. So, all our NMR experiments now depend on basically this net magnetization. This is what we use to finally record the spectrum. So, remember this is nothing but a difference coming from the population in the upper state minus the lower state, and that is depending on from the lower state minus the upper state is shown here beta, and the lower state is the upside which is alpha, and this difference in population contributes to this. So, therefore, if the population are equal, then this will be 0, because then everything will cancel in all directions. So, one can actually calculate from the Boltzmann equation at what temperature or what magnetic field or what conditions can the population become equal. You can also achieve a negative z axis. So, I can achieve a opposite thing where the population in this state becomes more than the population in this state. So, that is called population inversion. So, that also one can find out at what spin temperature we can achieve that. So, these are all based on the Boltzmann law. Now, how do we now achieve the excitation? So, remember we have to take the molecules from the ground state to the excited state. So, for that we have to now invoke this called rotating frame of reference. So, what is the rotating frame of reference is as follows. We saw that there is a spin which is now oriented like this, it is revolving in this direction. This is the frequency, angular frequency given like this. Now, what we do is the RF radiation which we apply, the energy which we apply for excitation is also has this frequency omega. So, now if you picturize this, I am applying a radiation which is circulating. Remember we showed one example where a case where we can not case, but we should look at the equivalence between this wave and this wave. So, we saw that they are actually equivalent. So, So, you can actually visualize, you can imagine that this radiation is actually the same radiation shown here. So, it is rotating with the angular frequency, which is the frequency of the wave, that is omega 0, omega equal to gamma v 0, and at the same time our spin is also precessing around the magnetic field. So, both of them are going around in this direction in the same speed. So, this is called resonance, on resonance. So, what has happened is, if you go to the frame of reference of this particular magnetic field which is rotating, then this spin appears static, because we remember we looked at an example that if two trains are moving at 100 kilometers per hour, and if you are sitting on one train, for you the other train will look static, it is not moving at all. So, the same thing is happening here. If you go to the frame of rotating frame of reference, a frame of reference on with this magnetic field, for that particular, in that particular frame of reference, this molecule looks, this spin looks static. So, this is called on resonance. So, when we do that, what happens is this spin now starts moving around this magnetic field. So, when it is static, we are representing the magnetic field. Now, this magnetic field is no longer rotating, because we have removed that rotation by going into the rotating frame. So, now whatever happens to the spin is from the point of view of the new frame, and in that new frame it is only looking at this magnetic field, and it starts moving around this magnetic field now, around this vector which is shown here. Okay. So, in the rotating frame we say that this magnetic field effect has gone, because we have removed the nullified that effect by going into a frame of reference which is the same with the spin. So, we no longer have this rotating precession. What is precession is only in the around this particular magnetic field, which is the radiation which we have applied. So, this is what happens, that now if you look at the bulk magnetization, so you have all the spins together. When remember we saw that we get a net magnetic vector which is shown here in the red color. So, what we do is we apply RF radiation, suppose we apply it along y axis, along the y axis. So, in the rotating frame the spin is now static, and then it starts tipping or moving around the y axis. So, this is what is shown here, that you have a magnetic field now which is a B1. So, what we remember in NMR, we use the B0 for this external magnetic field which was applied along z axis, that is the main magnetic field. But the small magnetic field which I applied, that is that RF radiation has a magnetic component, and that amplitude of that field, the strength of that field is given by B1. So, what happens now in the rotating frame is that this vector moves moving around this B1 value, and that is what happens. So, when it comes by 90 degree, we say it is a 90 degree flip angle. So, it has flipped by 90 degrees. When it comes by 180 degrees, we say it is flipped by 180. Similarly, when it comes by 270, we say it has 270, and then finally it goes up. So, this is how the B1 field is applied, that is external another magnetic field, a small magnetic field. Remember, this is in the value of kilohertz, and the external magnetic field we saw it is in the value of megahertz. So, it is almost 1000 times smaller compared to the main magnetic field, more than 1000 times. So, this is a very tiny small magnetic field applied, and the spin starts moving around that magnetic field in the rotating frame, and we stop the experiment when it is 90 degrees. So, when we stop when it is 90 degrees, that becomes a 90 degree pulse. Then once you remove this pulse, it is called as relaxation. So, what happens is the spins are now all together. So, when we applied a pulse, we brought the magnetization from this side to this side by a 90 degree pulse. So, that is called a 90 degree pulse. But this is not a situation where it is in equilibrium, it is come this side because of our application of a pulse of energy. So, it has to go back to its original situation. So, this vector when it goes towards like this and then it goes towards this way, remember the motion is never like this, it never goes like this, it always comes, the magnetic vector comes like this and then goes up, and that process is basically as it is going this side, it starts building up this side. So, simultaneously when it is coming this side goes up, and that process of building of the magnetization along z axis is known as T1 relaxation. And there is another process known as T2 relaxation, which is called dephasing. Why is it dephasing? So, if you look at this picture again, they are all distributed around this cone. So, this is called random phase, they are all phased out, they are not together, so they are all dephased. But when you apply a pulse, they all come together in this axis. So, they are got phased now. So, they have to go back to this scenario, this situation, because that is the equilibrium. So, this is called return to equilibrium, that is the we say it is relaxation. So, when it goes back, it has to achieve this position. So, this process when it goes from here to here is called T2 relaxation. We will see that in the next slide, what is shown here. So, this you start from this position, which is the 90 degree, and it starts dephasing around in the xy plane, and that is what we said is T2 relaxation. Also is shown in this picture, you can see that it starts. So, this is looking from the top view. So, this circle is in the xy plane, okay, z is coming out of the plane. Okay. So, this is coming out of the plane towards you, whereas this is the xy plane. So, you can see the vector starts dephasing, and slowly after a long time they are completely dephased. This is looking from the top view. So, this is called T2 relaxation, and this T2 relaxation is very important because it contributes to the line width. So, remember all the peaks with an NMR are never a single line, they will always have a width, and that width is coming because of the T2. So, typically it is proportional related to 1 over T2. So, if T2 is long, means if it takes long time to happen like this, then this line is very sharp, it will be tall. But if this from here to here, if it happens very quickly, then this line will be very broad. So, it will be something like this. So, the T2 determines the line will be fat or it will be narrow. And then this during this process of dephasing and at the same time going back towards z axis, we keep a receiver coil, and that induces a current in this coil, and the current EMF in the coil, and this EMF decreases to 0 like this, because at the last end of the time this completely magnetization is dephased and nothing is in the xy plane, everything has gone to z axis. So, basically the signal has completely dephased and it has become 0. So, this is what we saw, we call it as a free induction decay. So, this free induction decay, now you can do a Fourier transform and then you get a spectrum or a peak. So, this is what we saw, that the oscillation, this oscillation is basically coming because the magnetization is rotating in the xy plane, and it is also dephasing. So, dephasing part is captured by this decrease, and the oscillation is captured by this frequency here. The oscillation is coming because of chemical shift. So, that is what we capture in by Fourier transform, we get a peak corresponding to this oscillation frequency. So, this is what the total NMR experiment is done. You take a molecule, a sample which in NMR tube, this is what we typically concentration is a millimolar, we will see more in the next few slides, and then we actually apply a radio frequency pulse, and the radio frequency pulse is what I showed you, is basically depends on the 90 degree pulse, and that tilts the magnetization to the xy plane, and when they start going back towards the z axis, they start relaxing, and that induces a current in the coil, and that is called FID, induces a EMF in the coil, and that is called a time domain signal because it is with respect to time. So, as the signal is going to 0, it is time, and now this oscillation or this frequency is because of the chemical shift. That means each atom in the molecule will have a different chemical shift, and if you have three different hydrogens, for example, we saw in ethanol, the 3 different hydrogens will have 3 different frequency value, but remember they all combine together, and this process of Fourier transform separates them into 3 different peaks, and what you finally see is a spectrum. So, this is the entire process of NMR conceptually, starting from the spins to the spectrum. Now, this in the next class we will look at how now we record this experimentally this data, although we have already seen how a hardware looks like, but what are the practical aspects of recording a spectrum, and then how do we interpret the NMR spectrum.